Good day, and welcome to our webinar on right-sizing pumps with variable speed drives, brought to you by CFE Media and Technology and sponsored by Lenza. Joining us today will be Eugene Vogel, a pump and vibration specialist at EASA, the Electromechanical Authority. I'm Kevin Parker, editor of Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. Bigger isn't always better, and that's certainly true with centrifugal pumps. An oversized pump may run rough, hot, and absorb a lot more energy. Engineers and managers may try to improve pump efficiency by reducing the operating speed with a variable speed drive or VSD. This can work in some cases, but not in others. In this webinar, you'll learn how system curves interact with the pump curve to indicate the efficacy of applying VSDs to centrifugal pumps. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted on CFE Media websites with the on-demand version of the webcast. The exam is for one RECEP ASIC Certified Professional Development Hour. To get the best results from the webcast platform, please make note of the following. For technical problems, click on the question mark at the top right-hand corner of the screen to bring up a list of system checks to make before escalating to an online technician. If you experience issues with the slides or audio, please refresh the browser or click the Refresh Media button under the presenter's headshot. Volume settings can be controlled by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If a technician is needed, type a message into the Ask a Question box, and someone will get to you as quickly as possible. The Ask a Question box is also used to ask the speakers questions. Ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides and certificate of completion, use the Event Resources box on the left-hand side of the screen. You can download the presentation and certificate of completion until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. At Lenza, as a global specialist in motion-centric automation, we offer products, drive solutions, complete automation systems, engineering services, and tools from a single source. We are one of the few providers in the industry who are with you through the entire development process of your machine, from initial ideas to the after sales, from the control system all the way to the drive shaft. I'd now like to introduce our first speaker. Eugene Vogel is a pump and vibration specialist at EASA, St. Louis, Missouri. EASA is an international trade association of nearly 1,800 firms in about 80 countries that sell and service electromechanical apparatus. Before joining EASA, Vogel operated his own business, General Maintenance Equipment Engineering Incorporated, a marketing service and training organization for industrial maintenance and related technologies. Among other courses, he taught a pumps and pump systems seminar. He also has extensive background in vibration and dynamic balancing and chaired the St. Louis chapter of the Vibration Institute from 1993 to the year 2000. Gene, welcome to today's webinar, and please go ahead.
Thank you, Kevin. It's a pleasure to be here. Welcome to everyone. The topic today, how to interpret pump and system curves and see what their impact is on varying the speed of the pump with the intent to save energy, as a topic everyone's probably familiar with. and many of you may also be familiar with pump and system curves. For those who may not be familiar with pump and system curves, we're going to do a little quick review here in the beginning to set the stage, and then we'll explain how those interact and the impact that they have on when you vary the speed of the pump. Okay, so just to get things in scope, a pump is a device that changes mechanical energy, mechanical power, into hydraulic power. The mechanical power is torque on a rotating shaft and speed of the rotating shaft. And when it's changed into hydraulic power, that becomes the head, which is analogous to pressure, and the flow, which is the volume or quantity of the liquid that's pumped. There are a lot of different types of pumps out there. The two general categories are positive displacement and rotodynamic. Positive displacement pumps do not have pump curves. They have a constant relationship between pump speed and volume. But the rotodynamic pumps, both centrifugal and axial flow, do have pump curves. It's these rotodynamic pumps that have pump curves that we're going to focus on today. There may be some opportunities for energy savings with positive displacement pumps and variable speed applications, but those are not part of the subject today. So we're going to focus in on rotodynamic pumps, both centrifugal and mechanical. A centrifugal pump is one where the liquid is accelerated from the center of the impeller towards the outside. So the flow is from the middle outward on a centrifugal pump. When you need to adjust the flow through a centrifugal pump where there's too much flow and I need to reduce it, one way of doing that is to trim the outside diameter of the impeller. That's a very common practice with centrifugal pumps. The pump is trimmed to match the flow rate desired for the particular application. When you trim the outside diameter, you reduce the tip speed where the liquid is leaving the impeller, right at the outside diameter at the tip. Another way of reducing that tip speed and reducing the flow and head through the pump is to reduce the rotating speed without having to trim the impeller. So whether you trim the impeller to a smaller diameter or leave the impeller at its full diameter and run it at a slower speed, the effect is very, very similar, in fact, virtually identical. So either method can be used for adjusting the capacity of a pump. Axial flow pumps are also rotodynamic pumps, and they have a pump curve. There's no opportunity here really for trimming the outside diameter of an axial flow pump, but reducing the speed will change the head and flow characteristics of the pump and can be used to adjust the size of the pump, if you will, to a particular application. Here's a basic pump performance curve. The flow can go anywhere from 2,500 gallons per minute down to zero. The head can go from 0 up to 250 feet of head. And you could adjust it, for instance, by closing the discharge valve. The head is the axis on the left-hand side is vertical. The flow is the axis along the bottom, the horizontal. So if I got this pump and I close the discharge valve down, I could adjust the flow to, say, 1,800 gallons per minute, and at that point I'd have 200 feet of head. Does everyone see the operating point is about 1,800 gallons per minute and about 200 feet of head? If I continue to close down the discharge valve, I can actually shut down the flow of the pump completely and have zero flow. We refer to this as dead-headed. Now the pump is still running, but there's no flow through it. So open the valve back up, and the flow will increase. So I'm using a flow control valve, a discharge, or a throttle valve to control the flow through the pump. And if I open it all the way up, it goes up to about 2,500 gallons per minute for this particular pump, and I'll have about 40 feet of head. Now the efficiency of this pump changes throughout that range of flow. The efficiency, in fact, if I close the discharge valve down completely, it would be zero. But let's just close it down here a little bit. And as I close it down, the efficiency will come down. to a best efficiency point. It was 85%, and then as I continue to close it, it'll go all the way down to 0. Now, that makes sense to everyone, I hope. If I've got 0 flow at that point, the discharge valve is completely closed. The pump's still running. I'm putting energy into the pump, but I'm getting nothing out. The efficiency is 0. As I open the discharge valve and flow begins to go through the pump, the efficiency has to increase. I'm beginning to do some work. And it will continue to increase as I increase the flow until it gets to the point that we call the best efficiency point, the BEP, the best efficiency point. On this pump, that occurs at about 85%. Now, beyond this, I can continue to open up the discharge valve and get more flow. I'll get more flow through the pump, but it's going to take more and more and more energy to get it because the efficiency is going to be dropping. Efficiency will never make it back to 0 because there is some work being done by the pump. So efficiency is a function of the amount of flow through the pump, and there is a best efficiency point. Let's see where. All right. There's a very important formula that governs this relationship. The relationship that I'm showing you is a relationship between the flow, which is the horizontal axis, the head, which is the vertical axis on the left-hand side, and the efficiency, which is the vertical axis on the right-hand side. So I have those 3 parameters. Q in this formula is for quantity or volume or flow. H is for head. BHP is the braking horsepower. The little Greek character down here, teneta, stands for efficiency. So really simple formula. Incidentally, the SG on the end is for specific gravity, but the specific gravity for water, and let's just assume we're pumping water because it makes it easy. Efficiency, the specific gravity of water is 1, and if you multiply by 1, we don't have to worry about it. So we have this very simple formula: flow times head, divided by a constant, in this case 3960, and then divided by efficiency equals horsepower. If you just take flow times head, flow in gallons per minute, head in feet, and multiply them together and divide by 3960, you've got the gross amount of horsepower represented by the energy that the pump is producing, that it's absorbing. But of course the pump isn't 100% efficient, so when I divide by that efficiency, that eta down there, I then get the net power required. If you're working with pumps, this is a formula that you should know and use frequently. So if you look at a pump curve, what do we have? We have flow, we have head, we have efficiency. So if we have those 3 for any point on the curve, we can use that formula and say, hey, I've got power as well, so now we've added the power. These are the 4 parameters that are displayed on virtually any pump curve that you'll run across: flow, head, efficiency, and power. So the best efficiency point is one of the focal points of the information presented on the pump curve. In addition to the best efficiency point, there is the allowable and preferable operating range. It's going to be really difficult, and everybody would like to, but it's going to be difficult to get a pump size so it matches perfectly with the best efficiency point. And in fact, the flow may change and the head may change throughout the operation, especially if it's pumping, for instance, out of a sump where the sump level is changing. The head's going to be constantly changing as the sump level changes. So there is a range across which the pump will operate. We like to keep that range within the within the allowable operating range, and under no circumstances do we want to get outside of the allowable operating range. I'm not sure, I might have misspoke. We want to stay within the preferred operating range, and we definitely don't want to exceed the allowable operating range, as illustrated here. The effect of being outside the preferred operating range is a significant loss in efficiency and some other bad things that happen with the pump that we'll talk about here in just a minute. I'm not going to read you this slide, but take a second and read through that. The impact of being very far away from the best efficiency point is going to have an impact not only on your efficiency but also on the reliability of the pump. I noticed that last point there, even the load on the bearings the radial load on the bearings is increased as you get away from the best efficiency point. Anyone have questions on that? Okay, with that understanding, here's a pump curve. A typical pump curve, we can see our 4 parameters on there. We have the flow and the horizontal axis. We have the head on the vertical axis on the upper part of the graph. In this particular one, the efficiency are the green isometric lines, and the brown dashed lines are isometric horsepower indications. So a little different presentation of the same information that we saw before. In this case, I hope everyone can read the graph. We're looking for an operating point illustrated by the little upside down red L. We're looking for an operating point at 400 gallons per minute and 125 feet ahead. And it should be evident that the efficiency on this operating point is not very good. While the best efficiency point for this pump is out there at 77.5%, we're operating well outside of even the preferred operating range and pretty close to the limit on the allowable operating range. The efficiency, if you can read those green lines, goes from 76 down to 65, and by the time you get over where we're operating, we're down pretty close to 50% efficiency, which means about half of all the energy we're putting into this pump is going into heat, vibration, noise primarily. This is a 6x4 pump. 6-inch suction line, 4-inch discharge, 13-inch impeller. It's a 4-pole motor running 1780. Here's a different pump that does. This pump is provided with a 13-inch impeller, and it's been trimmed down to about a little over 11 inches, right at 11 inches, to meet this particular operating point. It could be trimmed down as far as 9.5 inches. Alternately, we could change the speed of the pump to do about the same thing. And although these are not equivalent numbers, just to illustrate changes of speed, a change between 1,300 RPM and 1,100 RPM would be roughly equivalent to the change between a 13-inch impeller and an 11-inch impeller, and the same down to 9 inches. Here's a different pump. There's a smaller pump. It has a 4-inch suction line and a 3-inch discharge. An 8-inch impeller runs its 2-pole, 3,500 RPM. And it has a flow rate of 400 gallons per minute and a head of 125 feet, same operating point. But notice how close to the best efficiency point this pump is operating. In machinery, people tend to have the idea that bigger is better. You want that V8 engine in your truck, but really all you need is a 6-cylinder. In pumps, too big is not good. Bigger is not better. The smaller pump in this case is going to run more efficiently. Imagine that you're talking with your pump supplier. You're going to replace a pump. He asks you for the head and flow, and you think, well, I don't know it, but it's blue. And the pump supplier says, well, if it was your blue pump, have a model number, and you give him the model number. He says, I got a couple of pumps here that'll do that. He says, I got the big, heavy pump with the 6x4 suction and discharge lines, running 4-pole motor, runs 1,800 RPM. Or I got a smaller pump, not as heavy, runs to 3,600 RPM. And I said, well, what's the efficiency on those pumps? And he said, well, the best efficiency pump on a bigger pump is 77.5%. And the best efficiency point on a smaller pump is 65%, 66%. I said, well, I want that nice big heavy pump with that better efficiency. Well, wait a minute. Not at our operating point. At our operating point, the efficiency is 50%, and the pump's going to run warm and the pump's going to run rough. Much better off with the smaller pump. So when sizing pumps, a lot different than sizing a lot of other machinery. It's got to be the right size, not too big. So where a pump actually operates, for instance, why does this pump operate at 400 gallons per minute and 125 feet ahead? That's determined by the system curve. The system is the combination of pipes, valves, heat exchangers, anything that through which the liquid flows other than the pump itself. The operating point is going to occur at the intersection between the system curve and the pump curve. The intersection between the system curve and the pump curve will be the operating point. So let's take a look at what goes into developing a system curve so you'll have a good idea of what that is. Here's a typical system. It has 360 gallons per minute is the design. That's what this particular operation needs. They need 360 gallons per minute. There's a suction tank that's above the pump, so there's a little bit of head, a little bit of pressure coming into the pump. And then there's a discharge tank that's much higher. It's going to pump the liquid out of the suction tank up into the discharge valve. Okay? So typically when you set up a system curve, you evaluate all of the suction side parameters or elements, and then you evaluate all of the discharge elements, and the total dynamic head is discharge head minus suction head. Let's just go through that quickly. Here on the suction side, we've got 6 feet of elevation, so we got 6 feet of head coming into the pump. That's helping us. That's a positive. Okay. We have to develop some velocity head. We've got to get that liquid moving, and that's going to cost you 1.3 feet of head. We got some friction through some pipe. 20 feet of 4-inch steel pipe loses 1.7 foot. We got an elbow. We lose a half a foot through the elbow or so, and a couple of isolation valves through which we lose a total of about 0.3 of a foot. Okay, well, let's total that all up. We started with 6. We had to take off some friction. Got to add a little bit of velocity head in, and we end up with a little over 4.5 feet of head net for the suction side. Let's do the same thing for the discharge side. And incidentally, that's at 360 gallons per minute. Let's do the same for the discharge side at 360 gallons per minute. We got 30 feet of elevation, so we got to pump that liquid up 30 feet. Okay, we got to get it moving a little faster, so we got to put some velocity head in. We got 35 feet of pipe, and it's only 3-inch pipe, so we lose 13 feet through the pipe. 13 feet of head loss through the pipe. We got an elbow, lose a little bit through it. We've got a globe valve. The globe valve loses 25 feet of head. If you're not familiar with what a globe valve is versus a gate valve or a butterfly valve, do some homework and look into that. If you've got a plumber that doesn't know the difference and puts in a globe valve instead of a gate valve, your system's not going to perform the same way. So that's a pretty high loss right there. Let's add those all up. What do we get? 75 feet ahead on the discharge side. I got 4.5 feet coming in as a positive. I got 75 on the other side. What's the difference between the two? The total dynamic head at 360 gallons per minute is about 70.5, 70.6 feet of head. Okay. Now, when I did those calculations, everything was based on 360 gallons per minute. There was some multiplication that was done. There are friction constants for all the different parts. They call it a K for the different elbows, and there's a pipe loss from pipe loss table. Those are multiplied by the flow rate of 360 gallons per minute, and I'm not going to do that on a calculator. I'm going to put that in a spreadsheet and put all those formulas in there to do the calculations for all the losses and just total them up. 360 gallons per minute at the top, 70.5 feet of head of loss dynamic head at the bottom. Why don't I take that column, since it's a spreadsheet, and copy it and paste it about 6 or 7 times? And now I've got a spreadsheet that shows me what the total dynamic head at the bottom of the column is for any flow rate entered at the top of the column, and I've conveniently entered 100, 200, up to 800. Now let's highlight that top row, and let's highlight the bottom row. Click that little icon on your spreadsheet that says, hey, I want to see this in a graphic format, and you have a system curve. So what are the axes on a system curve? The vertical axis is head. The horizontal axis is flow. Wait a minute. We had a pump curve. We had a pump curve that had the same vertical and horizontal axis. Why don't we just plot the pump curve and the system curve together, and the point of intersection is the operating point for that pump? Everybody see that the operating point is the intersection between the system curve and the pump curve. clean it up a little bit and make it a little bit clearer. In this particular illustration, if you look at the horizontal axis, our operating point occurs at about 700 gallons per minute. Let's suppose, for illustration purposes, that that's a little bit too much. You know what? We're pumping beer. This is a brewery, and we're pumping beer, and the brewmaster says, man, you can't pump that at 700 gallons per minute. It's effervescing too much. We're going to end up with flat beer. Slow it down. He says, don't pump any more than 600 gallons per minute. I don't know why anybody would want to pump less beer, but that's what he says. So we need to get that back to 600 gallons per minute flow rate. What do? One thing you could do would be to close a discharge valve called a throttle valve and throttle the flow. When we close the discharge valve, we bend the system curve. We bend the system curve. There's our operating point. We bend the system curve back and up because we've introduced more friction into the system, more head loss into the system. Okay? What's the effect? Well, we did reduce the flow. Okay? We moved it up. We moved it up the pump curve. We changed the system curve to move the operating point back up on the pump curve. To do that, we reduced the flow, but we increased the head. Well, if we reduce the flow and increase the head, what do we do the amount of power that's required? We had a formula for that. It was flow times head. One went down, one went up. What's the result? We don't know. It could be a little bit better. It might be a little bit worse. But it's not going to change really significantly. The power required at the lower flow rate is going to be somewhere close to what it was at the higher flow rate. Probably no real savings. So the other opportunity we said, if you recall, we said there's two ways to reduce the flow. You could either throttle the throttle valve, close the throttle valve and throttle the discharge, or we could lower the speed of the pump. If we lower the speed of the pump, we move the pump curve down along the system curve. When we throttle the pump, we move the system curve up the pump curve. That's throttling. This is what you get when you change the speed of the pump. You reduce the speed of the pump. So what happens to head and what happens to flow? They both go down. Well, if the horsepower is flow times head and they both go down, what do we know has to happen with the power? It has to go down. If we reduce the amount of power that's required, we will save the energy that would have been used by throttling the pump instead. Any questions on that? Okay. Well, there are different types or different shapes for system curves. Most of them, virtually all of them, are bent in this direction because the friction increases exponentially, but some can be shallower than others. And the determining factor on that typically is how much static or elevation head are you pumping. So the pump curve on the bottom, this marked zero elevation head, is probably a circulating system. And the one on the top, this marked mostly elevation head, is something that's raising liquid up from one level to another. So here's some typical applications that help define that. Friction head dominated system. The typical one is a thermal circulation, HVAC system. I'm pumping chill water, I'm pumping hot water. And I might be pumping it in a building up 3 or 4 floors, but it comes right back down through another pipe, that same 3 or 4 floors. So net, there is no elevation change. I'm simply pumping the liquid around in a loop. So there's no elevation head developed. Pipelines tend to be mostly friction. The Keystone pipeline pumps downhill. If you hooked it up to a tank on the top and you opened up the bottom, it actually would have some liquid coming out of it, not very much, so they use pumps to speed that flow up. The pumps primarily overcome the friction through the pipeline. A lot of your manufacturing processes are do very little elevation change and are mostly because of all the piping it takes to get the liquid, to get the beer from the brewery over to the chiller. It's the length of that pipe that they're overcoming. Irrigation is a case where there's typically a lot of friction. You may not be lifting the water very far, but you're running it through sprinkler heads or whatever. So there's a lot of friction. Static head dominated systems, primary water intake, you're pumping it out of a lake or a river, pumping it up into a reservoir. Cooling tower is a good example. They take the liquid out of the bottom of the cooling tower, pump it up into the top, dump it out. The only thing it does is lift the water. Sewage lift stations are a classic example. Pressure mains, it's not an elevation, but there's still a static head because you'd have to overcome the pressure in the main before you can pump anything into it. So they also fit into that high static head category. So you can see the difference between the shape. The mostly elevation head applications have a very shallow system curve. The shallow system curve indicates high elevation. Look at zero flow. At zero flow, there's 160-some feet ahead. We're not pumping any liquid through the system, and I still have to overcome the 160 feet ahead because that's how high the discharge is away from the suction. And the zero elevation head at zero flow has zero head. They don't move the liquid. There's no friction. That affects how much energy can be saved by reducing speed. In the case with mostly elevation head, it doesn't take a lot of change in speed to reduce that flow rate quite a bit. So there's a change in head to do that, but it's not very much. Okay, it's a pretty shallow curve. On the other hand, the zero elevation head, to make that same change from 700 gallons per minute down to 600 gallons per minute is a much greater change in the amount of head. In both cases, the amount of flow changes from 700 to 600. With the shallow curve, not much change in head. With a much deeper, steeper curve, much more change in head. Here's a circulating system. Looks like it's a school circ water system for their chill water, heat water. It may go up a few floors, but it'll come right back down. It's just one big loop. Okay? These are the systems that have the most opportunity for savings from variable speed drives. An elevation system, on the other hand, does not have as much opportunity for savings because the head is not changed as much. Also, on many of the systems that are high lift, high elevation applications, you have the opportunity to turn the pump on and off rather than control its speed. That also limits the amount of savings that you could get from a variable speed drive. Another advantage I think is just worth mentioning here, one of the problems that you run across sometimes on controlling flow is that you're pumping out of a sump and you want to have constant flow. He wants to keep that flow out of that beer vat at 600 gallons per minute, but as he's pumping it out, the level in the vat drops from 15 feet down to 4 feet. So that change in suction elevation reduces the positive head. The total dynamic head is suction minus discharge. So if you reduce the suction, you're going to increase the total dynamic head. So variable speed drives can accommodate that by changing the speed, increasing the speed of the pump as the sump is emptied. You can maintain constant flow. Worth mentioning. I've used care here to talk about variable speed drives. Many people can consider VFD instead of VSD as a variable speed drive, but that's only one of the different types. It's worth mentioning there's different types of variable speed drives. Certainly varying the frequency on an AC motor will change its speed, a very common, easy retrofit on an existing installation. But there's other options as well. The eddy current clutches have a very clean and easy to maintain system for varying speed. DC motors, although they're rare, do an excellent job of adjusting speed. Internal combustion engines, steam and gas turbines are all cases of variable speed drives. So, reduce the pump speed, you reduce the head, you reduce the flow, you reduce the power. Reduce the power, you reduce the energy and usage costs, and you get a bonus. One of the problems that plague pumps is cavitation. Cavitation occurs when bubbles are formed. Boy, that could really be a problem with beer. When the liquid comes into the pump, the pressure drops, bubbles form, and the implosion causes cavitation, or is cavitation, which damages the pump. When you slow the pump down, the tendency to cavitate is greatly reduced. So you get a bit of a bump, get a bit of a bonus. Let me show you on some actual pump curves, if I could, what that looks like. Let me get one up here. Okay, we've got an application. Just 1 second. All right. Can everyone see a pump curve on their screen? Okay, this application is looking for 368 gallons per minute at about 67, almost 70 feet of head. Okay. Suppose that we needed to reduce this flow rate from 368 down to 200 gallons per minute. Okay. We could do that by closing a valve. If we did that, and let's come right over here and say, you know what I need? I need to take this 368 and I need to get it down to 200. Say update, and that goes up to 73.4 feet of head at 200 gallons per minute. So we will have moved up the pump curve to 200 gallons per minute. Right about there. We've increased the head, we've decreased the flow. And what happened to our power? Our power went to 5 horsepower. At 368, our power was 7 horsepower. So we saved a little bit. We throttled the pump, we closed the valve, and we saved a little bit of horsepower from 7.3 down to 5.5 horsepower. As an alternate to that, what would it do if we reduced the rotating speed? If we come up here to the RPM, and I bring that down, there's 1760. Notice that the pump curve is moving down the system curve. And we want to get it down to 200 gallons per minute. Coming down, coming down, coming down. We're getting sort of close. Here we are at about, that intersection now is about 240. I need to get it down here to 200. Coming close. So let's bring that right down there to right about, just about got it. There we are. 200 gallons per minute. At 200 gallons per minute, I'm only now at 20 feet of head. And what happened to my power? 1.2 horsepower. I really reduced my power. Just to review. Should be back on slides. Okay, here's where we started. Where are we at here? Whoop, one more. There we go. Okay, little over 7 horsepower. We closed the throttle valve. We bent that curve back, and we got it down to 5 horsepower. But instead of doing that, if we go back to the original curve, and instead we move the pump down by slowing its speed down, we bring it down to a little over 1 horsepower. Can we get that into dollars and cents? Sure. We started with 5 horsepower. If we throttled it down to 200 horsepower, We got it down to about a little over 1 horsepower if we use speed control. That's a reduction of 3.9 horsepower. We can convert horsepower to kilowatts, both measures of power, 746 watts per horsepower. So that's equivalent to 2.9 kilowatts of power. And let's say we're running this 2,500 hours a year. That's just a little bit over one shift, just a little bit over an 8-hour shift for a year. And we're paying 15 cents a kilowatt hour for energy. Just do a little simple multiplication. You've saved yourself $1,000. You've got about a 10 horsepower motor on this to handle anything that it could possibly run across. Put a bigger motor on it. So you got a 10 horsepower variable speed drive. Can you buy a 10 horsepower variable speed drive for $1,000? Maybe. About the right price. 1 year payback? That doesn't sound too bad. Some other things that happen when you reduce the speed of the pump. The actual efficiency of the pump may go up or down. So you really need to look at the pump curve and the system curve to see what the effect is going to be. The changes in efficiency will move it somewhat. By slowing the pump down, if you get a little bit less efficiency, you might not have quite as much savings, but the reduction in both head and flow will more than overcome any minor losses in efficiency. And in fact, with some pumps, when you slow them down, they actually have the efficiency improve. It could go up, it could go down. One of the other impacts of reducing the speed, all machine structures have frequencies they like to shake at called natural frequencies. And if you slow the speed of the pump down until some component of that pump excites a natural frequency, you have resonance and you're going to have high vibration. If you're going to be adjusting machine speeds, you should be prepared to deal with possible potential mechanical issues with vibration. And if you have a pump that's too big, like the one that we saw before where it was operating very close to its allowable operating range, slowing that pump down will not fix that problem. If a pump's too big, the only real solution is to replace that pump with a smaller pump that operates closer to its best efficiency point. Energy savings can be quite significant. This is an actual case from quite a number of years back. They were only paying 8 cents a kilowatt hour, pretty good utility rate, but they eliminated 75 horsepower of load by adjusting this pump speed and getting it running close to its best efficiency point. It ran 8 hours a day, 365 days a year, one shift all year long. $13,000 in savings. Can be very significant. Very significant. So there are other things you can do to control flow. We talked about throttling and we talked about trimming speed. As we said early in the presentation, you can also trim the impeller. And trimming the impeller will have just about the same effect as reducing the speed, but I can't run the lathe backwards and put the metal back on the impeller. Once you trim the impeller, it can't go bigger without replacing it. So if you've got applications where you need to control the flow rather than just achieve a lower flow rate, variable speed drive is an answer. Accumulators mean that you can run the pump for a while and then turn it off. If you can cycle a pump on and off, you can have virtually the same savings without having to change the speed of the pump. So systems with accumulators are not good candidates for saving money with variable speed drives. Bypass we haven't talked about. You see bypass on a lot of HVAC systems. With bypass, instead of using a valve to throttle the flow, you simply bypass that flow around a heat exchanger or whatever it is that the flow isn't needed through. So the flow is still being pumped. The advantage is you get to leave the pump operating very close to its best efficiency point. So there are some moderate savings, but not as much as if you can control the flow rather than go ahead and pump the liquid and bypass it. You're still having to pump the liquid. Here's a system typical of a lift situation, a high elevation system, high static head. It's a sewage lift station. If you look, the static head is between 30 and 35 feet, and the total dynamic head is 40 feet. So you've only got 5 or 10 feet of friction head, depending on the level in the sump, compared to 30 feet of head elevate. Mostly what this does is it takes the pumpage, it takes the sewage, and it pumps it up. That's its job. There's not a lot of friction in the system. So we looked at that pump curve. And let me switch back over here. I'll just do this live screen. And close this message. You connected. Whoops. I may have, can you see that? Do you see a pump curve on your screen?
Not yet, no.
Okay, then let's abandon that and let me see if I can get back to the presentation. And I'll just do it with slides. Okay, so here is, I was going to show you live, but I'll show you here just on the slides. Here's that pump curve and system curve for that sewage lift station. And we're looking for 368 gallons per minute, 34 feet of head. One thing we could do with this pump has had the impeller trim from a little over 6, let's see, I can't read on that. The impeller's been trimmed down quite a bit. What if instead of trimming the impeller, what if we changed the speed of the pump and left the bigger impeller on? Can you see that that would move the operating point, that's 5 horsepower, move the operating point up to there. There it is with the same operating point, but it moved it up onto the higher diameter impeller, but lowered the speed. The speed is now 1420 RPM, and we reduced the power from 5 horsepower down to 4.5 horsepower. So we saved a half of a horsepower. Some savings, potentially, but not near what we saw with the system that had the much steeper curve. And here's the other thing that happens with these types of systems. This system is set up to cycle on and off on a set of floats. So if I can turn the pump on, let it run for a while, and then turn it back off, I'll get virtually the same savings as if I had run it at a slower speed. So these types of applications don't loan themselves to energy savings for reducing the speed of the machine. They still use variable speed on sewage lift stations. There are some potential energy savings there, but nothing like what you'll find on a circulating system that has throttle control. All right, so Kevin, did you want to jump back in here?
Thanks, Gene, for a really first-rate presentation. We'll turn to our questions now. We have quite a few questions to present to you, but please, to our audience, if you have additional questions, please send it to us now. The first question, Gene, is, in a large pumping station application, how does control using valves compare to control using speed? Specifically, the response to demands, surges, and other system changes.
That's a good question, Kevin. Thank you for that. That's always a concern. You don't want to make a change that's going to make it more difficult to control your system. In fact, variable speed drives will produce a very quick response and a very controllable response to inputs from whatever operational controls are coming in. Literally, whatever controls the valve, for instance, that you might be throttling the discharge with, typically, if it's an automatic system, is controlled by a motor-operated valve. So you're starting and stopping a motor as that motor runs that valve up or down or closes it. It's not an instant response. The speed response from a motor that's set up properly, from a drive, variable speed drive, can be just as responsive and in some cases more responsive.
Thanks, Gene. Another question from one of our listeners. What are some of the impacts of retrofitting a variable speed drive on existing pumps? in terms of flow in relation to head, motor compatibility, range of acceptable reduction, and so forth.
Okay, well, the most common retrofit is a variable frequency drive. Obviously, if you're going to go from an electric motor to a steam turbine or to a eddy current clutch, then you've got quite a mechanical change to be made. That's a significant changeover. Putting a variable frequency drive on an existing AC motor is a pretty simple installation. And I'm looking for the question here. It's gone. What was the rest of the question? Could you read me the rest of the question again?
Just in terms of what some of the other kinds of variations could be. I'm sorry, that's my fault. What are some of the aspects of retrofitting variable speed drives on existing pumps in terms of flow relation to head, motor compatibility, and so forth? Okay,
I'll go through the flow. As you saw on the slide, the difference between throttling and variable speed drive, you get effectively the same results, but you're reducing the head primarily. That's what you're doing. You're reducing the amount of head. Throttling increases head, reducing the speed decreases head, and that's where your savings come from. We had another question up there that went away. There it is. The question, as you mentioned, BEP is 85%. What do you mean? Is 85% of closed head or what? If you looked at the formula that said flow times head divided by some constant, in our case 3960 equals braking horsepower. If you just ignored the efficiency part, that efficiency part was in there, you'd have the gross amount of horsepower that was needed. Let's say I do that, my head times my flow, and I'm not going to throw numbers out, but let's say it comes out to be, the total comes out to be 100 horsepower. I need 100 horsepower to run this pump to get that amount of flow and head. But wait a minute, the pump's not 100% efficient. So if I only got 100 horsepower coming in, I can't get 100 horsepower worth of hydraulic energy out. I know I'm going to lose something through the system. Okay, so let's say my efficiency is 80%. Okay, then I'm going to need virtually pretty close to 20% more energy. So maybe I need 120 horsepower in to produce that 100 horsepower worth of results out. Efficiency is the difference between what I put in and what I get out. So if I put in 100 horsepower and I get out 100 horsepower worth of head and flow, I've got a 100% efficient system. But if I have to put in 120 horsepower to get 100 horsepower worth of hydraulic energy out, my system may only be 80% efficient. You actually got to crunch those numbers to get them to come out right. But I hope that answered that question.
Thanks, Gene. The next question, I believe, is in relation to slide 33. And it says, can you please explain what is the green curve, the dash curve, and the black curve on the graph?
Yeah, I surely can. And 33. Yep, let me get right there. There we go. Now, can you see that? Can you see that slide?
I can.
Okay. If you're referring to this slide, green curve, dash curve, and black curve. Okay. The green lines are isometric efficiency. Think of it like a mountain. And the little circle there around, semicircle right there at 71, that's 71% efficient. If you're anywhere on that green line, you're 71% efficient. As the efficiency falls off and you come down to 69, 67, 64, you're walking down the mountain, and the efficiency is dropping off. So at our operating point, we're just right a little slightly above 64% efficient. Okay? The dashed line, and I'm not sure that this is the one that he was talking about. What if we got this one up here? Is this the one you may have been asking about? Because on this one it's got a dashed line. The green lines are the same. That's the efficiency, isometric. The little dashed brown lines are the power. And if you look as it moves from the upper right to the lower left, the power goes down. So this is also isometric, and it's like walking down the mountain. As you come down, you can see that your power drops. So the operating point in this case is somewhere, I can't read that slide. It's too small on my screen. You can probably see it on yours. It looks like it's between 25 and 20 horsepower. Is that correct? A little closer to the 25, so maybe 22 horsepower. Okay. Hope that answered that question.
Good. Well, I'm sure you took a good shot at it. The next question came in just after you were talking about how the system curve was calculated. And the question is, why is the velocity head added to the suction head?
Well, first of all, for anyone who may not be familiar, the velocity head is the energy that it takes to get water moving. Okay, or to get liquid, to get anything moving, to get the pumpage moving. So let's talk about water. So to get water, you got a water balloon. I want to throw it. I put kinetic energy in. So that water balloon has got that kinetic energy. When it gets to the other end, it hits something. Okay, and the energy is released and goes back to static energy or to pressure energy. So that's what velocity energy is. It's how much energy does it take to get that mass moving. If you took the pump out and opened the valves up, the liquid is going to flow into the pump. So the energy provided for the velocity head on the suction side, in this case, is provided by the flooded suction, the fact that the suction is a positive number. The suction head is a positive number. So if you took the pump out, the water is going to move. It ain't the pump that's got to provide the power to get the liquid moving. It's the gravity that does that. It's just the opposite if it's a suction lift. Okay? If it's a suction lift, then the velocity head is negative on the suction.
Good.
Let's see.
Next question is, lowering the speed looks good because it saves horsepower required, but what about the efficiency? Does the efficiency go down and negate some of our savings?
In some cases, yes. In other cases, no. It just depends on the particular pump and system curves and how they interact. Now, in most cases, the change in efficiency, it's not unusual for the efficiency to drop slightly when you reduce speed. That's not unusual. In some cases, it increases. In a lot of cases, it stays just about the same. But that change in efficiency is going to be minor compared to the savings versus throttling because of the drop in head.
Great, thanks. Another question, we'll try to get a few more in here. How does atmospheric pressure affect pump performance? For example, sea level versus 6,000 feet.
It has very little effect on anything that we've talked about because on everything that we've talked about in this presentation, both suction and discharge are subject to the same atmospheric pressure. And the total dynamic head is discharge minus suction, so if you put it on both sides, it makes no difference. Where it makes most difference is on cavitation, because cavitation occurs when the suction head is too low. That pump might run fine at sea level. Put it up on top of a mountain, you don't have as much atmospheric pressure. The liquid coming into the pump will volatilize easier. Its vapor pressure is much lower. So once those bubbles form, that's what cavitation is. So from what it can make a difference on a system that is pumping against a pressure main or against a pressurized tank, where only the suction or possibly only the discharge is subject to atmospheric pressure. But all the systems we've talked about, suction and discharge are both at atmospheric pressure. Same thing on both of them, makes no difference.
Final question for today. Are there any other issues related to return on investment for a variable speed drive or a variable frequency drive that you haven't addressed yet?
There are quite a number of them. One of them that I'll just mention because I know that it happens frequently is people will install a variable frequency drive on an existing AC motor, which is one of the ways of getting variable speed. and they'll encounter problems induced by the carrier frequency. It'll end up as shaft currents and actually damage the bearings in the pump or in the motor or the pump or both. So that's one of several that little gotchas out there. Nobody told you about that one, and there's a number of others. That might be another topic for discussion. Stumbling blocks when changing speed. A lot of those have to do with the particular method that you use to change the speed. That was a gotcha for variable frequency drives. Are there gotchas for going to DC motors? Sure. How about going to gasoline engines? You bet. There's all kinds of problems you get into. As far as the pump itself, the pump really doesn't care much. There's no real bad gotchas that I can think of off the top of my head. Most of them have to do with whatever you're using to vary the speed.
Good. We have a number of additional questions, most of which also include the comment that this was a really excellent presentation, so I want to compliment you on that, Gene, as does the audience. And we'll have the answers to the unanswered questions when we post the archived version of the webcast. Thanks to our expert panelists, and thank you all for attending today's webcast. We hope it suited your purposes. For more information, go to the website link noted in the interface. I'd like to thank our sponsor, Lenza, for today's webcast. And now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it as we use this information to improve our webinars. On behalf of CFE Media and Technology, we'll see you next time.